the concept of shortest distance. Welcome, everyone. Today we are beginning a new topic, the concept of shortest distance. Now, before we dive into the formulas, let's set the stage. When we first started studying geometry, finding the distance between 2 points was quite simple. You just applied the distance formula. However, as we move into the study of three-dimensional or 3D geometry, things become a bit more complex. The distance between two lines is not always as straightforward as the distance between 2 points. You see, unlike points, which are fixed, lines extend infinitely in all directions through space. Because they go on forever, we can't just pick any 2 points and call it the distance between the lines. Instead, we focus our attention on what we call the shortest distance. This represents the absolute minimum possible gap you could find between any 2 points belonging to the respective lines. In the next few slides, we will define exactly how we identify this minimum gap and how it behaves when lines are not parallel. Defining the shortest distance. Now that we've established that 3D geometry involves looking at the gaps between infinite lines, let's get a bit more precise with a formal definition. Suppose we have 2 lines, let's call them L sub 1 and L sub 2, existing in three-dimensional space. To understand the distance between them, let's pick any random, arbitrary point on the first line and label it P similarly. Let's pick any arbitrary point on the second line and label it Q. If we draw a straight line connecting these 2 specific points, the distance between them is simply the length of the line segment PQ. But here is the important part to remember. Because these lines extend infinitely, we aren't stuck with just one pair of points. As we slide point P along its line and move point Q along its line, the length of that segment PQ will constantly change. It might get longer or it might get shorter depending on where the points are located. So, when we talk about the shortest distance, or SD, what we are actually looking for is the absolute minimum value that the length of PQ can possibly reach among all the infinite possible pairs of points P and Q. Keep this idea of a minimum value in mind, because in the next slide, we'll see how this concept becomes even more specific when we deal with lines that never meet, known as skew lines. The case of skew lines. Now that we have established that the shortest distance is simply the minimum gap between any 2 points on 2 different lines, let's look at a much more interesting scenario. While the concept of distance can be applied to any 2 lines, it becomes particularly fascinating when we encounter what we call skew lines. Now, you might be used to 2D geometry where lines are either parallel or they intersect. But in 3D space, we have these skew lines, which are neither parallel nor intersecting, and importantly, they do not lie in the same plane. They are essentially passing each other in different layers of space. What makes skew lines so special is that there is one, and only one, unique line segment, let's call it PQ, that represents this shortest distance. There isn't a range of minimum distances, there is just one specific path. And why is this segment unique? It comes down to a fundamental geometric property that you'll need to remember for your calculations. The shortest distance between 2 skew lines is exactly the length of the line segment that meets both lines at a right angle. In other words, the shortest distance is measured along a line segment that is perpendicular to both lines. We will explore why this perpendicularity is so crucial in the next slide. Why must it be perpendicular? Imagine we have a line segment connecting a point on line 1 to a point on line 2, but this segment is hitting the lines at an angle. It's not perpendicular. If it's slanted, it means we haven't found the tightest possible connection yet. If we were to slightly shift our endpoints, point P or point Q, along their respective lines, we could actually straighten out that segment. By moving the points toward that perpendicular position, we effectively shrink the gap, creating a shorter segment. It is only when the segment reaches a state where it is perfectly perpendicular to both direction vectors that we can no longer shorten it by shifting the points. At this specific orientation, the segment reaches its absolute minimum length. In geometry, we give this special, unique segment a specific name. We call it the common perpendicular. Keep this term in mind, as it is the key to everything we are about to visualize in our next example involving air traffic control. Now you might be wondering, why does it have to be perpendicular? Let's think about this logically. Real-world analogy, air traffic control. Now, I know that the geometric definition of skew lines can feel a bit abstract and difficult to picture in your mind. So, to help you visualize this concept, let's step away from the coordinate planes and look at a real-world analogy, air traffic control. Imagine you are looking up at a vast, open sky. In this scenario, we have two airplanes flying their respective routes. First, let's look at airplane A. It is flying along a perfectly straight path, which we can represent as line L1, maintaining a steady altitude of 30,000 feet. Next, we have airplane B. This plane is also flying along a straight path, which we'll call line L2, but it is cruising at a different altitude of 35,000 feet. Now, here is the crucial part. These two flight paths are not parallel, they are heading in different directions. However, because they are at different altitudes and moving on different trajectories, they are also not heading toward a collision point. They are essentially skew in relation to one another. As we will see in the next slide, even though they never meet, there is still a specific minimum gap between them. Step-by-step visualization. Now that we have the mental image of those two airplanes flying at different altitudes, let's break down exactly what is happening in that sky to connect this analogy back to our mathematical theory. First, think about the variable distance. Because both planes are moving along their own paths, the distance between them isn't constant. At one moment, they might be miles apart. A few minutes later, they might be much closer. The distance is constantly changing as they progress along their respective lines. Second, even though they are moving, there is a moment of maximum proximity. There is one specific point in time and one specific pair of positions for airplane A and airplane B, where the gap between them reaches its absolute minimum. This is what we are searching for when we calculate the shortest distance. Third, this brings us to the most critical geometric concept, the common perpendicular. If you were to freeze time at that exact moment of closest approach and draw a straight line connecting the two planes, that line wouldn't just be any line. It would be perfectly perpendicular to the flight path of airplane A, and it would also be perfectly perpendicular to the flight path of airplane B. Finally, the length of this specific perpendicular segment, this bridge between the two paths, is exactly what we define as the shortest distance between the two flight paths. This perfectly illustrates the principle we discussed in the previous slides, that the shortest distance between two skew lines is found along their common perpendicular. As we move into the next slide, we will summarize these key takeaways to ensure you have the core concepts solidified. Key takeaways. All right, let's bring everything we've discussed so far together. We've looked at the moving points, the concept of skew lines, and that great airplane analogy, so now let's summarize the key takeaways you need to remember for your exams. First, let's revisit the general definition. Remember, when we talk about the shortest distance between two lines, we aren't just looking at any random gap. We are looking for the absolute minimum length of a line segment that connects any arbitrary point on the first line to any arbitrary point on the second line. It is the smallest possible value you can find. Second, this brings us back to that crucial property of the common perpendicular. As we saw in our visualization of the airplanes, for skew lines, the shortest distance isn't measured at a random angle. It is specifically measured along a line segment that hits both lines at a right angle, meaning it is perpendicular to both lines. Third, it is important to note the uniqueness of this segment. For any two skew lines, there is only one single, unique common perpendicular. You won't find multiple different segments that all satisfy this perpendicular property. Finally, let's look at the geometric significance of the value we calculate. This is a very important logical point. If you perform your calculations and find that the shortest distance is equal to 0, what does that tell you? It tells you that the gap has vanished, which means the two lines must actually intersect at a single point. Now, before we move on to the next slide, I want to highlight some common pitfalls where students often lose marks, so please pay close attention to the following. Common mistakes to avoid. First, please be careful not to confuse specific points with the lines themselves. When you look at the equations for two lines, you will often see position vectors, which we call a sub-1 and a sub-2. A very common error is to simply calculate the distance between these two specific points. Remember, the distance between these 2 points is just one possible distance among infinitely many. It is not necessarily the shortest distance we have been discussing. Second, avoid the assumption that non-parallel lines must intersect. In your 2D geometry classes, you learned that if two lines aren't parallel, they eventually meet. However, as we discussed in the section on skew lines, 3D space is much more complex. Lines can be non-parallel and yet still never meet because they exist in different planes. Always check if the lines are skew before assuming an intersection point exists. Finally, never ignore the perpendicular property. When you begin deriving formulas or solving for the distance, always keep in mind that the shortest path must be perpendicular to both lines. If you lose sight of this common perpendicular property, your entire conceptual approach to the problem will likely be incorrect. Now, as we wrap up this lesson, I want to pause and highlight some common pitfalls. Even students who understand the concept of the common perpendicular can sometimes stumble when solving complex problems. Keep these points in mind, and you will have a much stronger grasp of 3D geometry.